Hi, I want to just quickly review the circuit elements that are used in the physics textbook Surway and Jewett's Physics for Science and Engineers 9th and 10th editions. Now, most of these symbols are pretty standard, but one of the things with standards, what electrical engineers do, what physicists do, sometimes varies, and sometimes there aren't universally agreed upon symbols. Now, the symbols that I have in the left and center columns are symbols that are used all of the time from chapters 23 through chapters into, well, the 40s when we start talking about other types of circuits. So a basic line that you see in any circuit diagram represents a wire. For a battery, there tend to be parallel lines with a long line followed by a short line, and I describe it as looking like a Donkey Kong ladder from the old 1980s video game Donkey Kong. So the reason why I say that is the bar on the top is positive, so you can imagine increasing the potential difference with your battery by climbing up the ladder or decreasing the potential difference by climbing down the ladder. Now a capacitor is represented by two parallel lines because the basic geometry for a capacitor is a parallel plate geometry. And often in a circuit diagram, if it's important, you'll see the positive plate of a capacitor labeled, but that's not always going to be the case. Usually with capacitors, they'll be designated with a C standing for the capacitance, and if there are a whole bunch of elements, there'll be a number designating which capacitor it is in the legend of that circuit diagram. Now, for resistors. Resistors are back and forth zigzags. You'll see them listed with an R. Again, if you have multiple resistors, you'll have numbers corresponding to which resistor. You can take a look at a table, and you'll often want to note the direction of the current going through that resistor. Even if it's not necessarily given to you, it's something that you would be guessing in solving a circuit problem, because as you go with the resistor, you would be subtracting the potential difference if you go with the current. You would be adding the potential difference if you go against the current. So you can think about a resistor as kind of like being a slide. If a battery is a ladder, you go with the normal flow of traffic, you're going down a level. Against the flow of traffic, you're going up a level. And the last circuit element we commonly use are inductors. And an inductor looks like a little solenoid, a little coil. It'll be labeled with an L, and again, sometimes you'll see the direction of current noted in that inductor, because as you go through an inductor with the direction of current, again, there would be a reduction in the electrical potential difference based off the EMF of that conductor. The final element I want to point out is a switch. And the symbol that our textbook uses for a switch is a line, usually with an arrow that's set at an angle to denote an old school Frankenstein movie bayonet style switch, where if you close that switch, current can go through. If it's open, there's a physical break in the circuit preventing current. Now, often you might see what looks like a little upside down Christmas tree. That is a universal symbol meaning electrical ground, which means we're saying the electrical potential of that point is set at 0. So if we're raising potential above the wire that has this upside down Christmas tree attached to it, we'd be at a higher electric potential. Below that, we'd be at a negative or lower electric potential. Now, there are a whole bunch of non-standard elements that you may see folks use. If you're talking about just a generic power supply or just a generic piece of equipment, it's common to circle something and put something in the circle to denote what it is. So for a DC power supply, I've most commonly seen a plus minus in the circle to signify the fact that there's a positive side and a negative side to that supply. For an AC power supply, there's usually a tilde, because with AC, you have an oscillating electric potential difference, which leads to an oscillating current. For metering, you'll usually see meters with a V or an A in a circle. V for voltmeter, A for ammeter, which measures current, and a voltmeter would always be hooked up in parallel with an element you're measuring the voltage of. An ammeter should always be hooked up in series with an element you're trying to measure the current traveling through. Other things you might see, light bulbs. Light bulbs are often represented as resistors because really a light bulb is just a resistor that's designed to get really hot to the point where it glows. In the case of an incandescent, in the case of modern high efficiency bulbs, we have a different symbol that we'd often use for that. But for an old school incandescent light bulb, sometimes you'll see what looks like a squiggle of wire in a circle. That's not an inductor technically, though if the wire's wound, there is some inductance there. But it just represents the filament that you see inside a light bulb. For a diode, it's kind of like a one-way valve for current. So you see a little triangle with a bar next to it. It's kind of like one of those gates where it says, do not back up, severe tire damage. If you go in the direction you're supposed to path, it's fine. If you try to back up, you get stopped. That's how to read that symbol. Now, modern light bulbs are largely LEDs. And the symbol that's often used for LED is a diode with a little squiggly wave popping out, and that's because LED means light emitting diode. So it's a diode that emits light. There are many other circuit elements that you might run into. We haven't even talked about what happens if we were to have an element that makes or is made up of many diode junctions, a transistor. But these 6 that I highlighted over here are the big 6 for the case of physics and what we're doing with it this semester. But if you're going into electrical engineering, take a look at the elements you see in a circuit diagram, and if you're ever unsure, ask someone, because we try to do roughly the same thing, but there really isn't a universal standard for everything, just like there isn't a universal standard for the notation we use for talking about concepts. Thanks for watching.